This video covers permutation and combination calculations along with knowing when to use a permutation or a combination. Let's begin by defining permutation. Permutation is the number of ways n objects can be arranged when r items are used and the order of the arrangement matters. So the notation is P for permutation, parenthesis, n is the total number of items available, comma r is the number of items actually being put into an arrangement, and this equals the calculation of n factorial over the quantity n minus r factorial. The difference between permutation calculation and combination calculation is that the combination calculation will have an extra r factorial in the denominator. Now the reason that it has an extra r factorial in the denominator is that with combinations, order does not matter. Let's take a look at the definition of combination. It is the number of ways n objects can be arranged when r items are used and the order is disregarded. So, for example, if we had a line, the line of Suze, Bob, Cal, if I had that as a lineup, Suze, Bob, Cal, that would be considered the exact same as Cal, Bob, Suze. Order doesn't matter, there's still three people. All right, now let's take a look at actually calculating these. To begin with, I'll show how to do them by hand, and then I want to encourage you to use technology. Let's start with the calculation of the permutation 5 taken 2 at a time. So we have 5 items, but we're only taking 2 of them and putting them in arrangement. So I have n is 5 factorial, over the quantity n, which is 5, minus r, which is 2. This becomes 5 factorial over 3 factorial. Now, if we know the definition of factorial from a prior lesson, we can see that 5 factorial is 5 times 4 times 3 times 2 times 1. And 3 factorial is 3 times 2 times 1. Like reducing fractions, if I have a factor in the numerator and in denominator, they reduce out. That means I'm left with 5 times 4, which is 20. If I have 5 items, and I'm taking only 2 of them at a time, I can put them in 20 arrangements. If I were to look at this with some other techniques that we've used before, I have 2 items, I'm putting them in an arrangement where I have 5 to select from. So I go 5 in my first slot. Now once I've placed one of my items, I only have 4 to place in my second slot. Multiply it together, I can also get a 20. Now I used technology on this earlier and I arrived at the answer of 20 also. Part B, combination of 5 taken 2. So this time we're taking 5 items, only going to take 2 of those 5 items, put them in a line or an arrangement, but the order does not matter. So this time there'll be fewer altogether. Formula is n factorial over r factorial times the quantity n minus r factorial. Means I have 5 factorial over 2 factorial times the quantity 5 minus 2 factorial. Now I write this out in a simplified manner. Write the factorials out in their meaning. I can reduce the 3, 2, and 1. I can also reduce the 4 with 2. That leaves me with 5 times 2 in the numerator, which is 10, and 1 in the denominator. So my answer is 10. The combination of having 5 things but only taking 2 of them, putting them in an arrangement where order does not matter, I end up with 10. Now let's take a look at 2 word situations. The reason I like to look at 2 word situations is that deciding if a problem is a permutation, combination, or a fundamental counting principle is actually the most difficult part for students. The calculations themselves aren't difficult because we can use technology to do the tedious work. Now, one thing that I keep in mind when I'm working with these problems is for a permutation, we know the order matters. So an example of that is if I had to put together a lineup for a baseball team. There's a specific order for a lineup, and so I know that order matters. Also, if I was putting together a music playlist for a wedding and I had the father-daughter dance, and then I had the couple that just got married dancing, and I had the groom and the mother dancing, then I'd have specific songs that I had picked, and that would be a particular order. So that would be a permutation. Now, maybe I have a playlist on Spotify and I hit shuffle. Now that order doesn't matter because I hit shuffle, and it could be all sorts of different ways as long as the playlist is played. That's a combination when the order doesn't matter. But if the playlist matters, it's a permutation. Okay, example 1. There are 3 committee positions: chairman, secretary, and treasurer. How many ways can the positions be filled from a selection of 31 people? All right, I see that I have 31 people, and I know that I have 3 committee positions. And these committee positions have an importance. If I was chairman, that would be a very different position than if I was secretary or if I was treasurer. That means this is a permutation problem. The order matters. It matters who is chairman versus who is secretary. There's 31 people to select from, and there are only 3 committee positions. So doing this by hand, I can see that it's 31 factorial over 31 minus 3 factorial, or 31 factorial over 28 factorial. And this would simplify down to really be 31 times 30 times 29, because everything from 28 on would reduce out with the denominator. When order matters, the answer that we arrive at is 26,970. Example 2. At the frozen mousse, there are 31 toppings to select from. Now, I made that number up. It's probably not accurate. Well, we've got 31 toppings to select from. If only 3 toppings are to be selected, how many ways can the toppings be selected? Now, this problem doesn't specify or indicate that the order of the toppings being put on actually matters. And most of us would say, no, it really doesn't matter what order toppings are put on. So this is a combination. It's a combination of 31 toppings, but I can only select 3 of them. And this would be 31 factorial over 3 factorial times 31 minus 3 factorial. This simplifies down to be 31 factorial over 3 factorial times 28 factorial. Now, similarly to the one up above, this would simplify down to be 31 times 30 times 29, and then all the factors from 28 down would reduce out. But there's also other factors that are going to reduce out, or at least be reduced. And that's because we have this 3 factorial. 3 factorial is 3 times 2 times 1, or 6. And this 6 can reduce with the 30 to make that a 5. Because it has an extra set of factors in the denominator as compared to the permutation, this answer is 4,495. So we can see that the order not mattering really reduces the number of arrangements that can be made.